Okay, today is our second big dose of probability. Probability is probably hard, okay? With probability 1, it is hard for most people. So I'm going to try to give you just the highlights, the key parts. But if you plan on doing the SLAM course next semester and you're a robotics student, you'll have just enough to survive. So that's the idea. You'll learn a whole lot more in the first couple of weeks of the SLAM course. If you're not taking that and you want to learn more probability, EECS 501, random variables and random processes, EECS 501. So what we're doing is setting ourselves up to move into the Kalman Filter, which is a recursive minimum variance estimator. So you guys did RLS with nils, so that was recursive weighted least squares. So if you chose your weight matrix appropriately, it was recursive best linear unbiased estimator is what RLS was, depending on how you choose the weight matrix. If you take the weight matrix to be the information matrix coming from the noise perturbations on the measurements, then RLS is recursive blue. Kalman Filter is recursive MVE, minimum variance estimator. Okay, so were there questions on the very first 2 pages on random variables? On what is a probability space? What's the space of events going on there? That kind of work? Question, yes?
It makes it up that the field is close to countable units intersections that complement. Is it close to
Okay, so our probability space has 3 elements, sort of like when we defined a norm space, we had 3 elements. So this here is the set of all events that can possibly occur. And the question is it closed under arbitrary unions and arbitrary intersections? And the answer is no. Okay, so in general, if you have a collection of events that is indexed by the counting numbers, then any of the standard set operations applied to those needs to give you, once again, an element in the set. In mathematics, those are called sigma algebras, but we don't care. So yeah, so the answer to the question is F. If A1, A2, AN up to infinity, countable are in there, then you can do intersections of those, unions of those, things like that. But if this is indexed by the reals, and so you have an uncountable number of intersections, that may not then be an F, and you may not be able to assign a probability to that event. Okay, so, I mean, you don't care, probably, excuse me, likely you don't care, but you know, if you look at all possible subsets of just the reals, it's extremely, extremely complex. So if you're wanting to have a natural notion of the size of a set, and let's just work on the interval 0, 1, for example. You would want that size to be such if you had an open interval or a closed interval AB that the weight was B minus A. We're in the set 0, 1, okay? Everybody agree you'd want the size to be proportional to that, okay? So the thing is, you can write down subsets of the reals for which no such notion of length is compatible with having the length of something like the interval AB being B minus A. So the algebra of all the subsets of real numbers is extremely complex. And so this here is just so that you only take nice operations and you start with nice sets. For us, since we're dealing with densities, the way I like to think about it is the kind of sets, if you can figure out what the integral is over that set, so if you take and write it as a disjoint union of some sets, you guys know how to do an integral over that set. If I give you something like, I don't know, the Cantor set, which you've never heard of, you would not know how to do the integral, okay? Because you've never heard of it, but it's got an uncountably infinite number of elements in it, and you would not know how to calculate the integral. So with the sigma algebras, all we're saying is we're only assigning probabilities to nice sets. And for us, they tend to be things that look like this. If we have a normal random variable, a really beautiful event would be the set of all possible outcomes that are within one standard deviation of the mean. And the likelihood of that event occurring is 68%. If you put 2 standard deviations, it's something like 92% or something, okay? So the events are subsets of our domain for the random variable. So if you're doing a normal random variable, the domain is minus infinity plus infinity, the real numbers. But we're not going to assign probabilities to every possible subset of that. F just gives the set of sets we're doing it with. Okay? Other questions?
I have a notation question on the second page, the A. It has the power of C, and I'm not sure why they wrote it like that, or what exactly does C mean?
Yeah, so they is me, so.
Yeah, you.
Yeah, that's okay. So this is, you sometimes see the set complement written like that. I typically put a tilde in front of it. So whatever you're used to using, x greater than x is the complement of x less than or equal to x. So the set of all omegas satisfying this is the complement of this set. So the tilde just means set complement. You're free to use whichever notation you were taught. And so because the sets that we're assigning probability to include this, they also include the complement. And then you get intervals because that's the intersection of one of these sets and its complement and stuff like that. So just kind of giving you an idea that you can build up a pretty rich set of events and assign probabilities to them. Another question?
First page?
Yep.
Just a little, so A is an event. Is A a field or is A, does it grow or sigma?
So any subset of here is called an event, but it may not be an allowed event. Yeah. So, you know, I can write down something as a subset of the real numbers, but I may not be able to assign a probability to that. It could be such a crazy contorted set that I can't make sense out of. Well, no, that's different. This would be sets that I would build with uncountable operations on opens, intervals, and things like that. So I can build super complicated sets for which this Riemann integral and even the extension, the Lebesgue integral, no longer even makes sense. I don't know how to add up. This is supposed to mean a sum. And if the set I put down here A, so the probability of X being in A has to be, you know, I'd go back to my thing and I try to look at my description of A and I try to add up all the area underneath it. That's what an integral is in principle. that can be so complicated that I can't really make sense of the sum as a limit of things that I approximate. So it's hard to imagine unless you've had a course in measure theory, but that's what's going on here. That's why that complication is there. So for us, you know, closed intervals, disjoint pieces and things, all this kind of stuff we would normally encounter, they're all nicely measurable and they'll be in our set of allowed events. We can assign a probability to them. Cool. Yes?
So that third bullet point says that F is a collection of allowed events and it must at least contain a null set.
Yeah.
What does that mean? Because if it contains other things in addition to the null set, then
Well, the empty set is the complement of everything. So if the sigma algebra is going to include that the probability of the entire sample space is 1, and your thing is supposed to be closed under set complement, then we need the empty set in there as well. So these are your sigma algebra, your collection of allowed events has to contain at least that. And then if you're dealing with a dice, well then omega would be something really simple, as we were saying. It'd be 1, 2, 3, 4, 5, 6. And F would be subsets of that, so 1 and 3 would be in there. 5, 6, 7 is not, because 7's not in there, things like that. So this is just telling you that at least it has to have something so I can assign the probability of 0 to the empty set, and the probability of 1, that's the normalization to the whole set. I have a feeling I'm not answering your question.
I think it's okay. I'm mostly just curious that if we have the space of like all possible events as contained in omega, then like I don't know how saying that it must contain the empty set, which doesn't have any elements in it.
Well, in principle, F could be empty itself, I guess, okay? Then I'm not assigning probabilities to anything. So F is a subset of the set of all subsets of omega. It's not every, F in general is not the power set for omega. It's not the set of all subsets. That set is too big. I don't know how to assign probabilities to it, especially when I'm doing continuous random variables, because I have no clue how to do an integral over something, you know, intervals, that's trivial. Disjoint unions of intervals, trivial to do integrals, but you can define integrals over more complicated sets. And that's all we're doing here is the sigma algebra is giving us the type of sets where we can look at probability of the set of all omega in omega such that x of omega is an element of A. I need that to be the integral over A of the density. And some A's are too complicated to make sense of this integral. That's all that's going on here. Okay? So, okay, and so to have a continuous random variable, this set of events, F, needs to contain the set of all omega such that x is less than or equal to some little x for any x. And then because it's closed under set complement, we get it for x greater than, and because it's closed under intersections and unions, you can see you can put x in some pretty interesting things, and you calculate the probability of those events by doing the integral over the event. So this x less than or equal to x would be from minus infinity to x and then some whatever dummy interval, dummy integral, dummy variable in the integral, and then you've got the probability with, and that's the definition of a density. Yep. Oh. Yeah, there's an X missing there. Yep. I looked for all the typos, but you know, yep. Otherwise, that's just one, okay? Without the X, that's one. Yep, all random variables that mean one. No, they don't. I'll fix that typo and update the handout. Thanks for pointing that out. Anything else? Okay, so that's, once we have that, then we can start moving on to random vectors, which are collections of random variables. So this is where we're going to be doing all of our work. We've done a little bit of this when we looked at blue and when we looked at the minimum variance estimator. So some of this is familiar. What we didn't need to do then was worry much about densities, and then the notion of conditional probabilities, we didn't need to do anything with that. And so that's really where we're headed in the short term here. So the first thing was just define a random vector to be something where each of its components is a random variable. So because xi is a random variable, this is an allowed event. Xi of omega less than or equal to the component xi here. That's an allowed event. And because our set of allowed events is closed under intersections, this is an allowed event too, and I can assign a probability to it. Okay, so what I mean by the vector x less than or equal to the random vector x less than or equal to the vector x is that this is true pointwise. So that's an and or an intersection of events. Okay, so just because we have a random vector, each component is a random variable, this is automatically something to which I should be able to assign a probability. And we just say that x is a continuous random vector if I can compute the probability of such sets by integrating a density. And you look at that and you go, wow, that looks like really fun, okay? So it's iterated integrals, but that's the definition of calculating the probability. And so as shorthand, we would often just write x is distributed as, so this is not meaning set complement here, fx. So it's just saying my random vector is defined by this density. So is the density uniform on the first component, it's normal on the second component, it's Laplace on the third, etc. How are they connected? So f has all the information about calculating the probabilities of various events. So we use this shorthand notation. Okay, so in general, you are used to writing sine of x as a Maclaurin or Taylor series, exponential of x as a Maclaurin or Taylor series, etc. So you can develop them in terms of power series. There are many, many densities for which you can, or random variables and densities for which you can do something similar. And so you take this g to be a monomial, x1 times x7, okay? x3 cubed, different powers of the x's. And those are called moments. So in general, you can put any function here, but the moments is mainly when g is a monomial. And so maybe you don't like working with the density, and maybe you could find some way to estimate a bunch of the moments, and then with that information, you could also characterize the density. For us, we only use 2 of them, and they're the same ones we've seen when we did blue and when we did the minimum variance estimator. We take g of x equals x, and we get the mean. Okay, so g of x equals x. And when we put just x1, we get the mean of x1. When we put just little x2, we get the mean of the random vector x2, etc. So those can be computed just by replacing g with xi, and you get the various first moments. So it's the mean of the random variable or the expected value of each of the components. You stack them up and you have the mean of the random vector. Then we've seen this already too. We try to see correlations and variances of the various components. So we take x minus its mean times x minus its mean transpose. This is a column vector. That's a row vector. So this is now P by P matrix. And it's positive semi-definite. If you want to check that, let's just do it. Let's let V be an RP, and I'll choose a less aggressive color. So we need to check V transpose sigma V greater than or equal to 0. If it's true, then sigma is positive semi-definite. Okay, so let's just do it. So V transpose sigma V equals V transpose expected value x minus mu transpose times V. So let's just take this inside, because expectations are simply integrals. We can take constants inside the integrals. Okay, so V transpose times x minus mu. So what we really have here is expected value of the vector x minus mu transpose times V transpose times the vector x minus mu transpose V. And so that's the expected value of the norm x minus mu transpose V squared. And so that's going to be bigger than or equal to 0. Okay, row vector times a column vector. We have a scalar, really. Now we have a row vector times a column vector, but this makes it super clear that we've got a vector. Bingo. So, and why is it positive? It's because we're doing an integral over omega norm x minus mu transpose V squared f sub x of x dx. And everything here is greater than or equal to 0. This is greater than or equal to 0. So the integral is greater than or equal to 0. Okay, so the covariance matrix is positive, semi-definite, symmetric, and all its smallest eigenvalue is greater than or equal to 0. Question, yeah?
Why do we have, like, what's the isn't the covariance just this? Like, just the x minus?
So this is the covariance, not the variance. So the covariance is a matrix, and we're just showing that that matrix is positive semi-definite. So we multiply by a vector on the left and on the right. We need that to be, for all possible v, to be greater than or equal to 0. Yep. So. Okay, so now this is where things start getting interesting, is when we start going here shortly, building up what are called marginal distributions, marginal densities, etc. So let me just try to scare the living daylights out of you for a little bit and then get you to calm back down. Okay, so we're going to need to take our random vector and break it up into pieces. Eventually for us, we're going to have to do it in 3 different pieces, but let's start with 2. And this is like something we're trying to estimate, and this is a measurement of it that we are making. Okay. Eventually, I want to understand how measuring this helps me reduce the uncertainty in this part. That's estimation. Taking measurements, reducing your a priori uncertainty in another quantity. That's what estimation is about. Okay, so let's first develop some notation. So when we have x1 and x2 as they're each random vectors. So P is n plus m. So x1 is an n random vector, and capital X2, so here's my second typo. Okay, is another random vector. So, you know, big block X, here's its density. Well, big block X is partitioned. It's often more convenient to write it as fx1, x2. So this notation means the same thing as this, and this means the same thing as this, okay? And so as before, where we're writing x has density f sub x, we'll often write the partition vector x1, x2 has density fx1, x2. Now, if you want to write the little x1 and the little x2, that's fine. For many formulas, it's convenient to just drop some of the arguments. Okay, so there's a variable that goes in the integral for the density with the first one, and there's a variable with the second one, and you don't have to call them x's. You can call them y's or z's or w's, whatever you want to call them. They're just dummy variables in the formulas for the densities. So when x is partitioned into pieces, we say the overall density is the joint density of the first piece and the second piece. So joint density of x1 and x2. So this is the first thing that could never happen if we're just doing a random variable, because if x only has dimension 1, you can't partition it into anything interesting, okay? So you need random vectors, and we're going to do the general case where each component can have arbitrary finite size there, so it's still a random vector. So with the random thing, when it's partitioned, it doesn't really change anything. It still has a mean. It's just that we break the mean up into the first part and the second part, okay? It still has a covariance, but it makes sense to partition the covariance into the part that's only associated with the first components, only associated with the second components, and the things that look like the cross information. Okay, so it's just partitioning the matrix according to x1, x1, x2, x2, x1, and x2, x2, and x1. So all I've done here is write down this, write down its transpose, do the matrix, the vector multiplications to get the matrix, and you can see, yep, that's a covariance of x1, yep, that's a covariance of x2, and oh, yeah, that's got something with x1 and something with x2. Okay, so this is just notation so far. And then there's one piece of vocabulary that you'll hear a lot. This part of the covariance matrix, people often call the covariance of x1 with x2. So you take x1 minus its mean times x2 minus its mean transpose. And it's called the correlation of x1 and x2. The correlation. So all we've got here is definitions. We just partitioned x, that partitions the mean, it partitions the covariance matrix. And then we get these off-diagonal terms. This is a block diagonal, this is a block. These off-diagonal terms in the generalized sense are correlations. Okay, so now if we assume the big guy is a random vector, then each of its vector components, those are random vectors as well. And if the first one is a continuous random vector and has a density, the other ones do too. Okay, so the density of x1 is called the marginal of x1, and this is the marginal density of x2. And so here's a new piece of vocabulary. The densities of the components of x have special names. They're called the marginals. Now you guys had to compute those in homework 2, I think it was. It was my chance to give you a heads up. There's some probability. And if you weren't a robotics student, maybe it was a reason to just check out. Robotics students had no choice, okay? You're stuck with the course. But 98 people took the midterm, so I guess most of you decided this was okay, a little bit of probability. So these marginals are just a nightmare, okay? For a general density, going from the joint density of x1, x2 to get the marginal that only depends upon x1, you have to integrate out all of the effect of x2. And if x2 has m components, this is m iterated integrals to get rid of the components of x2. And if x1 has n components, it's n iterated integrals. So going from the joint density to get the individual densities for general probability distributions is just no fun at all. No one ever wants to compute those, even numerically. They're just a nightmare. So in a little bit, when we do Gaussian random vectors, it's going to be very, very important to us that we can just read these off immediately. There are no calculations to do. You just write them down. I see the joint, now I have the marginals, okay? You just write them down. So that's what you really, 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 really want to get out of this. No fun in general. When it's normal, also called Gaussian, life is super sweet. Okay, so these marginals will be important to us. We get them easy. Another definition, concept, x1 and x2 are said to be independent random vectors if the joint density is the product of the marginals. joint density is the marginal of x1 times the marginal of x2. Now, a weaker notion is that x1 and x2 are uncorrelated if this sigma 1, 2 term that we had is the zero matrix. That's uncorrelated. Okay, now, let's just talk a little bit here. What type of functions do you know that when you, that you can easily factor like this? And the ones that work the best are exponentials. Okay? Because e to the x1 times e to the x2 is e to the x1 plus x2, right? So e to the x1 squared plus x2 squared plus x3 squared is the product of those things. Okay, so the Gaussian distribution, because it's based upon exponentials, makes this thing either immediately obvious that it's true or immediately obvious that it's false, as we'll see, okay? In general, taking this and asked if I could untangle x1 and x2 into a product of only x1 and only x2, also that's very hard. For normal, it's going to be very easy. And so definitely mark this, okay? It's free points on the final exam, and you need free points, okay? If two random vectors are independent, they are automatically uncorrelated. But the converse is false. Okay, so why would the converse be false? Well, this is only a property of the second moment. It doesn't say that the third and fourth and fifth and sixth moments factor too, okay? It's like looking at the second term of a Taylor series and trying to do something about all the other terms. In general, you can't do it. You just can't do it, okay? So it's only for normal random vectors, Gaussian random vectors, that these two things are equivalent. So if it's Gaussian, and that's on the handout, they're equivalent. If they're not, they're Laplacian or some other crazy thing, then these are not equivalent concepts. Okay, so we can take a big vector, partition it with a whole bunch of integrals, get the densities of its components. Okay. So to me, the other stuff is kind of glorified calculus. This is something different here, okay? So this is what estimation is all about. Maybe that's why estimation is hard. So conditioning, it's called. So the whole idea is I observe that this event happened. I want to know how that gives me more information on the probability of occurrence of this event. So, conditional probability of A. Given that B has occurred, its definition is it's the measure of A and B happening divided by the probability of B happening. So I need B to be non-zero, the probability of that being non-zero. That's the conditional probability of A given B. So let's just look at a few little simple cases. If B is contained in A, then A intersected with B is just B, and then the ratio is 1. Okay, so I know that something that my event came from B, then it certainly came from A. Bingo. I know for sure that that has happened. If A is contained in B, the opposite, okay, then A intersected with B is equal to A, but it's normalized by B, okay? Now, B is strictly less than or equal to 1, and it's positive. So this ratio is bigger than or equal to the probability of A, okay? How much uncertainty? Something happened from B, but I see here that 40% of B is in A. So now I know that 40% chance that I have a 40% chance that when I drew it from B, it also came from A. So I've increased my knowledge. Whereas, you know, this whole thing in omega, maybe even B itself is only a 10% occurrence. Okay, but my sensor tells me that it's at least within this region, and so that gives me a lot of more information about A. Before, A was only a 3% occurrence, okay? But now B has occurred, and now I know that now there's a 30% chance that the point really landed in here. Could have landed here, could have been drawn from here. That's what probability, what conditional probabilities are giving you information about. It's that one thing happening gives you a little bit more information about another. So that's sensor fusion. A, my robot state, its current velocity. B, I measure something from an encoder. I now have a position. Position doesn't give me velocity, but I know what my velocity was moving before, and so I can make a relative improvement to that velocity measurement. So it's sensor fusion. It's really what these conditional probabilities are all about. P of A is our current estimate of the probability our robot is in some certain place. We get a sensor measurement. P of B is kind of our relative confidence in that, and the conditional probability of how we fuse the two is these conditional probabilities. Windows Defender, see fewer notifications. That's the one I'm going to select. Oh my God. Come on, Windows. No, no, no. That's what I want. Okay, almost there. Okay, now I've got a split screen. Anybody get me out of my split screen? Please, please, be nice. There we go. Okay, we're back. Okay, sorry for the delay there. Okay, so that's for events. Let's go to random variables and random vectors now. So what's the equivalent when you have a density? So this is, we're getting closer and closer to the heart of recursion. So we still have our partitioned random vector. The conditional density of the first component of the vector, given that we measured the second component, so it's now a number. Okay? these are random variables, random vectors, they're functions, but I've now measured its value. Okay? That's like I know this event occurred. What event occurred? X2 came out when I measured the sensor. I measured my encoder. The joint is between two of the quantization levels of my encoder. With just the tiniest bit of vibration, it could have jumped one side or the other, okay? But I now have a number, okay? It was really in between the two things, okay? But the sensor gave a number. Which one did it give? It tossed a coin from the vibration world and it gave me a number. Given this number, what does that tell me about the density now of X1, given that I've measured the second component? Okay, so this is the same as P of A given B. So it's the joint density normalized by the density of X2 evaluated at the measurement point. So if you want to put a bar here to make clear that that's a number, feel free, okay? But X1 given X2, this is still a random vector, and this is its density. You change the measurement, and maybe you move the mean of X1 over, and you reduce the spread. Okay? So this is super, super, super important. I have X1, X2. I measure the second component. What does that tell me about the first? And it tells me its distribution, the density now of X1 is not equal to the marginal. It's the joint divided by the marginal of X2 evaluated at the point where the measure that I actually measured it. Okay. Question? Okay, so we'll often write this as X1 conditioned on X2. A conditioned on B. X1 conditioned on X2. Now, to be totally technically correct, I should always write X2 and then put the value here. But almost nobody does that, okay? You'll see it written shorthand like this, X1 given X2, and you have to know that there's a value. You have to know that there is a value. So that's still a random vector, and this is its density, the joint density of X1 and X2 divided by the marginal density of X2, that's the normalization, P of A and B over probability of B, it's the same thing. And then X1 is varying, but X2 is frozen at the measured value. 7, 3, 11, whatever, okay? X2 is a... Now, if X1 given X2 is a random vector that I can calculate as mean, and I can calculate as covariance. It has a density, so the mean is just X1 times its density. Remember, X2 is frozen. So integrating with respect to X1, variable here, X2 is fixed at the measured value. That's called the conditional mean. I also have a conditional covariance. What's the covariance of X1 minus its conditional mean, given that I made this measurement. So it's the same thing. I do this, transpose, and I multiply it by this density. That's conditional covariance. In general, giving me information about the X2 component should help me understand X1. Now, happens when the joint density is such that x1 is independent of x2? What happens when we divide by f of x2? We just get the marginal for x1, okay? So when they're independent, this thing is just the density of x1, and I get just the mean of x1 back. I would get just the covariance of x1 back. And measuring x2 tells me nothing about x1. But when they're correlated, they're mixed, they're not independent. Making the measurement gives me information about x1. So that's the concept to have in mind, is that conditional probabilities, conditional densities, is refining your estimate about the likelihood of A, given that you now know something about the occurrence of B. Refining your likelihood of the occurrence of x1, given that you know something happened in this component, and x2 and x1 are connected, they're not independent. If they're independent, then this is a product, this is one of the products, and you only get the marginal of x1. And fine, yeah, it's still a conditional probability, but it's not an interesting one. A little tiny bit getting through, sort of partially working.
Professor Green?
Yes, please.
So, from this, can you say that as long as you have two sensors that are not independent, and one is good and one is really weak, as long as you don't overestimate, or as long as you don't say that the sensor is better than what it actually is, you'll always at least get a little bit more information about your state?
Yeah, so the question is how can you get the right proportion of information out is the question. And we're going to have a formula in a little bit that's just going to make you see it, okay? So I'm going to delay the answer, but it'll have all of the right pieces of information. Okay, so we don't do the Kalman filter today, but I need to derive a couple of formulas. And if you see what the Kalman filter is doing, this calculation I'm going to make is going to seem super interesting. Okay, when you did recursively squared, the x was constant. Or when you had a forgetting factor, x was drifting slowly. So in standard RLS, x was constant. That means this was the identity and this was 0. Xk plus 1 equals xk. That means x doesn't change. Okay? Then you had a whole bunch of measurements. So now x evolves, it has dynamics. It has an initial condition. We'll have a probability distribution on the initial conditions. These are noise terms. We'll have probability distributions on those. And what we want to do is estimate x based upon the measurements. X is evolving in time. And we're getting these measurements. And these are coming from cameras, LiDARs, encoders, things like that. And we have relative information about their uncertainty here. So, people have developed some really cool notation with the Kalman filter. So, this is how they're doing the conditional expectation. So this is your best guess of the x at time k, given measurements all the way up to the current time. So that's the k is for x. It's evolving. And this is, at what point are you using the measurements? And we'll see why that's important. So it has a mean, and it has a covariance. This is the conditional covariance of x at time k, given the measurements of the time k. And then this is the recursion, the prediction ahead. This is my best guess of x at time k plus 1, given the measurements of the time k. So they're different, right? And this would be the conditional covariance of that. So this is what the filter looks like. We'll derive it on Thursday from scratch. Okay. But let's concentrate here on what we do when there is a new measurement. So this is the recursion part. This is our former best guess of x given the measurements up to time k minus 1. Now I want to make a correction in that based upon the measurement. Okay. What is this term here? That's my best guess of what the measurement would have been given my past measurements. I can predict what I should see from my sensor, okay? That's what that is. So that's the conditional mean and the conditional covariance. Now, I don't know, just really quick something. Take this term here. This is the Kalman gain, and multiply it out here. So take this term and put it here. What does that remind you of? Pure complement, okay? This is the uncertainty at time k, given the measurements at time k, is my uncertainty at time k, given measurements only up to time k minus 1. I'm predicting, okay? I'm being dangerous. I'm making a weather forecast, okay? But now I've actually taken a measurement. This is my reduction. When I put this term down here, that's my reduction in the uncertainty of my estimate. That's the sensor fusion, okay? So, I want to do this. I'm going to define the less aggressive colors. X, Y, Z. X looks like my little state K of the Kalman filter. Y is my measurement at time K. And Z is my measurement up to time k minus 1. Okay. If I put Y and Z together, I have all the measurements. Okay. I have YK minus 1, Y0. I'm trying to make an analogy here to Kalman Filter. Okay, now I have a random vector with not x1, x2. I've got 3 components. I'm calling them x, y, and z. Y is my most recent measurement, Z is the past measurement, and X is the thing I'm trying to estimate. I want to know this, okay? So, we want to compute condition of Y and Z. Right? That's X condition on all of my measurements, everything I know. So what is that? Y and Z, that's my X2. X, that's my X1. So this is the joint density of all of these guys divided by the density of y and z. This is my x1 and this is my x2, what we did 15 minutes ago. This is what I want to compute, that conditional probability. Why is that not good? This is batch process. Batch processing. This is estimating x with all of the measurements at once. That's saving them all up and doing the conditional thing, okay? This is like just doing weighted least squares and not doing recursive. See a recursive solution estimating the state on the basis of two sets of measurements. Okay. See the motivation for that? Let's go back to the Kalman filter and then we'll write something down. What is this? This is x conditioned on z that y0 to yk minus 1. Okay. X at time k, I call my capital S. And then this is my y conditioned on z. X, xk, y, my most recent measurement, z, everything from the past. That's what the Kalman filter is doing. That's what makes it recursive, okay? I just keep updating these, and I only do a correction to those based upon my latest measurement. Okay, so what we have lying around is x conditional z, y conditional z. Sort of, kind of, maybe, tenuously, c leading somewhere. So what I want to do is, how can I calculate this density with these two at hand? And that's what the Kalman filter is all about. Okay. Okay, so we have x and y conditions on z available to us. So that's the vector x condition on z. We have that. So this condition on z, that has density f, x, y, and z divided by the marginal of z. That's the joint. Okay. Whereas this one, that's f, the joint of x condition on z. Y condition. So what do we have?
we have, okay? That's what we're trying to do. We have X conditioned on the past, we have the most recent measurement conditioned on the past, we have their joint density. Here's the measurement, okay? Here's the magical solution. The joint condition Y condition is get joint density. Oh, sorry. I'm going to do from the joint density X condition on Z, Y condition on Z. I'm going to condition this component on this component. Let's see what we get. So XZ conditioned on Y. That's the joint X given Z, Y given Z over Y given Z. So that's how conditional densities work. Conditions for X1 on X2. So this joint is really X, Y condition density. This conditional is X, Y, Z joint divided by this, Z. X, Y, Z, Y, Z. This is F, Y, Z, Y, Z. X1 condition on X2 is the joint divided by the marginal of X2. You can apply that formula. The FC's cancel, and we have half X, Y, Z divided by Y, Z. That's the distribution of X given current measurement and the past. X given the current measurement and the past. Okay, so you guys are going to work this in homework 7 that you're working on now. This is like problem 6. You have to go through a case where you have a Gaussian vector with 3 components, and you have to calculate first this conditional density, that conditional density, then this one conditioned on that, and then you're going to calculate the joint X, Y, Z divided by that. You're going to calculate this, and you're going to see they're exactly the same. So this is going to be in your homework problem. Okay, but this is the recursive formula. This is the batch. This is X given the past, the current measurement given the past, and then a direct calculation involving those two. So this is the part of the recursion. In the Kalman filter. Okay, so your eyes about this big, or are they so squinted up because you're like falling asleep, okay? So you should either be like, it's blowing me away in amazement, or I'm just bored out of my soul. I can't believe I'm sitting in this room. Okay, so anyway, back to what we're doing. We don't want to calculate x based upon the entire past. What we want to have is, if we already estimated x based upon k minus 1, and we predict the next measurement based upon that, we want to take those two marginals and extract out x conditioned on everything. And the magic is x condition on y0 to yk minus 1, yk condition on y0 to k minus 1. That conditional density, which gives us the same answer as processing them in a batch. So this is weighted least squares, and up there was RLS. Recursive. This is just batch. Okay, let's drop that for now. Let's do something else just to save us some time so we can spend more time on the Kalman Filter Thursday. Simple facts about Gaussian random vectors. Everybody can read this without any problems. How we can a scalar random variable distributed. This is the multivariate normal distribution. That's the determinant of the covariance matrix. That's the information matrix. For this not to be dividing by 0, and for this to exist, the covariance matrix be positive definite. Okay, so the assumption here is covariance matrix positive definite. Most important thing to notice is completely described by the mean and the covariance matrix. That's all you need. You need two moments. First moment, the mean. The second moment, the covariance. Okay, that's all you need. It's completely described by two moments. It's an exponential. So if this matrix is diagonal, it's a product of exponential, because then this is just a sum of xi squared. And the exponential of a sum is the product of the exponentials. Okay? So if sigma is diagonal, then x1 is independent from x2 is independent from x3. Okay? So not being correlated and being independent follows from just the properties of sigma and exponential. Exponential is some product of the exponential. Okay. Once you're given the mean and the covariance, it replaces all of these integers. Instead of iterated integrals, read it out of, do your calculation, calculate mean and the covariance matrix. So, giving you mu and sigma replaces all of those integrals. The marginals, completely trivial to compute the marginal of each component. This is the term on the diagonal. The term on the diagonal is the variance of the ith component of my vector, and the ith component of the mean is the mean of the ith component. It makes it totally trivial to go from the joint to the marginal. All that information is in mu as a vector, mu1, mu2, etc. And then the diagonal elements, I equals j of the covariance. So that's simple. So the marginals, completely trivial. I want to spend more time on the linear combinations. So let me jump here just to answer the question earlier. So, information on x2 takes value of x2. Here's the mean. Let's just appreciate this formula, what it's telling us, okay? If x1 and x2 are uncorrelated, what is the value of this term? It's 0. Okay, we get no information about how we move the mean of x1 by making the measurement of x2. Now suppose the x2 component has a gigantic, simply gigantic covariance matrix, so the information matrix is really tiny. How do you adjust your guess of the mean of x1 based upon making this measurement? You just ignore it, okay? Because there's so much noise in this relative to what you have here. And so that's what's going on. This formula is telling you everything that you're asking for in terms of how do you do the relative weighting. If x2 has low variance, and you really use the fact that x2 seems to be far away from its mean to adjust where the mean of x1 is. So this formula in the Gaussian case gives you all sorts of beautiful information. And it says right here, the covariance of x1, once you've measured x2, is the sheer complement of the covariance of the x1 vector minus in the covariance of the whole thing. So this is the sheer complement of sigma 1 in the joint covariance of x1 and x2. There's the sheer complement. Okay, we've used up our time. We'll come back to this, but this formula tells you everything about how you use the data in the case of Kalman. Super. Thank you.